tabular data typically, a lot of tabular data doesn't just originate being just a single table, but a lot of it actually comes from databases with linked tables. And well, a company that has a lot of data of linked tables is SAP. So it's not surprising that they're working on foundation models for such tabular data. And of course, this is very tightly linked with the AutoML field. So I'm excited to hear the two of them speak. Johannes was meaning to come here in person. He had a family emergency. Still made it possible that Marco is here in person and he's online. So yeah, let's welcome them. Let's a big applause.
Hello, everyone. Excited to be here, or at least remotely. And thanks for the great intro. And yeah, sorry that I couldn't be inside, and I wish you a terrific conference. So yeah, let me start to give an overview of like what our goal at SAP is. Frank just mentioned it. We have lots of data, but also the goal is to actually create lots of AI functionality across our applications, right? And I think in that sense, it's really very similar to many enterprise applications of machine learning. So I hope you can also take away a lot for your own work here. So one concrete example, right, is to automate, of course, tedious processes that many of the business users go through. So just one example, if you are a business that sells stuff, right, then you get sales orders from your customers and you have to send them invoices. And in the contrast to kind of consumer-oriented selling in the business, it's usually the case that invoices are not always the same, right? The payment terms differ. By when should the customer pay? What's the target date? What's the maybe discount if they pay early? So all of these payment terms, you need to figure out based on the customer, based on the context, and you need knowledge for that, right? So it's a very simple feature, but it's something we can automate, and I want to use this a bit of as a driving example throughout the presentation. And you can imagine this is like one tiny feature now, right? One tiny capability, but we want to scale this across all the thousands of applications that people are using in the SAP space. And I think the critical piece, if we go to the next slide, to understand here, and the biggest hurdle is, and the biggest challenge is to understand the data that you want to build your model on, right? So this term of linked business data, I think it's really key to scalable machine learning. Of course, the data is where the models ultimately built on, right? So the event logs or the time series or the graphs, but the data is often cryptic, right? So you need to have the information available to actually make sense of the data. So for example, a database schema that tells you what a column actually means or what the table is all about. And sometimes even the database schema is cryptic, right? Especially at SAP, it's a company grown over 50 years. The old school database tables still have like 8 character names, right? So you can't even make sense of the database table names or column names. Similar, in the database tables themselves, you often have fields like the payment terms, which are of course not a string that tells like payable in 30 days or payable at a discount, but it's actually an enumeration, a categorical value that is linked to some other explanation in a data dictionary somewhere that you also need to actually make sense of the data. And last but not least, you need knowledge about the whole thing, right? Because even if you have the information available, you might not know how the data is being used, what the constraints are, what all the target values, the target labels are, and how they connect to each other. And if you're lucky, at SAP, we actually have business objects, so the domains are modeled, right? And the business objects are actually connected down to the database tables. So it's actually really linked business data, right? So it's you have this data at your fingertips. And to motivate this a bit, we can go through the example. So if you look at the lowest level, you really don't know what's going on. It's just a database table with lots of cryptic or empty fields. So you really need to look at the information. So the database schema, for example, tells you that the VBAK or VBKD, these are the table names of customer payment terms or sales orders. But the first part where I would say as a non-expert, where you get what this is all about is when you go to the view level, which is then called sales order, or where you really understand about the data is when you go to the business objects. So sales order, customer payment terms. So some domain experts really sat down and figured out what these objects are, but post hoc, right? So this was not done upfront. So the key challenge then is to understand this data, and only then can you scale to really go broad with machine learning. So if you look at the next slide, I think the key expertise required is really crossing disciplines. So you need the domain knowledge to identify the right piece of data, which is best known by the app developer. You need to collect the data from some data sources, and then ultimately you're at the machine learning level where you can apply AutoML methods. But I mean, it's common wisdom, right, that the domain knowledge and data collection is actually taking a lot of time, right? And I don't want to give any percentages here. I guess everybody can figure that out for themselves. But I really think we need to look at all these disciplines to scale machine learning. And the idea is now to really build a foundation model on both domain data and the actual instance data. So if we go to the next slide, just very, very briefly, the idea would be to take all the raw data, all the instance data and tables, time series, etc., and use the connections that it has to link business data, at least in some parts, some forms. It's of course noisy, but then in the similar spirit as for language models or other foundation models, to train in a self-supervised manner to do prediction of, for example, a graph representation of the payment terms by just blanking it out. And the hope is then that you actually get two main benefits. So if you go to the next slide, we would hope that by learning a lot across a lot of data sets over a lot of customers, that you learn patterns across customers and you can onboard new customers very, very quickly. So you basically get rid of the cold start problem, or at least you address it in parts. And on the other hand, I think that's actually even more important to from my opinion, is to have more domain knowledge in the model, so that hopefully the model itself can figure out which pieces of the data it needs and which connections in the linked business data world it should tap into to actually create a new use case, right? So instead of predicting the payment terms, you might want to predict the delivery date, right? Or the likelihood that the customer is not going to pay. Do you really want to set up a new model for each of these and create a new model? It's going to be a huge effort, right? So really reducing expertise and making this available out of the box is the key. So we would like to be in the top right corner here, which is, I guess, still a bit of an untapped field. So in the next slide, just like how could this look like if it works, right? And I think I would love to live in a world where this works, because then you could just dynamically add, for example, in a table that shows all your open sales orders, like when the expected delivery date is, when the expected delay is, as a customer, right? And you don't need anyone anymore to actually create the models for you. It actually automatically populates that, or very, very long term, to actually use this as a tool and for LLM-based digital assistants to answer questions that are about the future. So when will sales order, when will the item be delivered to Seattle? Will it be on time? And then the LLM translates this query to kind of a prediction query in the foundation model and would reply out of the box without any training. And this is kind of future music, very concretely, something that on the next slide would already make the lives of many customers easier, is to just simplify the UIs that are usually driving lots of business processes, right? I mean, I guess everybody who's worked at a company has filled out tons of forms on leave requests or reimbursement, right? And that's kind of the day-to-day work for every business user in a digitized business. And if you make this life a little bit easier by at least predicting some of these fields that are obvious, right? So you get a sales order in, where is the sales group located, to get recommendations and make this work. This is kind of one of the first like very concrete points where I think this could be very, very helpful to have such a model. So really to auto-complete in a very structured setting. So not auto-completion in a kind of dynamic document language setting, but in a structured setting. And with this, I want to hand over to Marco to dive more deeply into the technical and research questions. Thanks a lot.
Thanks, Johannes, for this introduction and for motivating why we need a business model, a foundational model on business data, on linked data. So we tried starting to think about this, and we identified several different requirements and difficulties that we have. So on the one hand, of course, data, it's always the main point in data science. We need to learn from multiple tables, which are related in different ways, but we also need to learn from multiple sources of data because to make sense of these databases, you need things like business data catalogs, and sometimes data is hidden behind APIs or data is inside views and not inside tables and so on. And sometimes you even have data which is not in a structured data at all because there are human readable descriptions of some fields or from tables which might also be needed in order to understand the content. Then we have a set of, let's say, hard requirements, measurable requirements, which are maybe what most people is familiar with, things like targeting high accuracy, of course, and also making solutions that work in a low data regime because so that we can easily move to new customers or new tables. And in a similar spirit, we would like to have solutions which can, to some extent, generalize across different use cases. And also, finally, that they are usable by non-experts. Otherwise, if our solutions are only usable by experts, then you are not better in the end than narrow AI solutions. And perhaps most importantly, to even make anything of this possible, we need to make sure that the data stay secure, and in particular, things like personally identifiable information and confidential data cannot leak. And we know that for generative AI solutions, this is often a problem, having the training data secured. So we have some work that we have started on this. We have created the model. So for now, we are working on single tables. So all the harder aspects of linked data that Johannes mentioned before is still not, let's say, in this slide. Here we are focusing on single table, so more of a classical setup. And we are trying to build a model which is a foundational model so that can be pre-trained on a large amount of data. And for such, we looked at the transformers, and in particular transformers encoders, because they have the nice property that they are permutation equivariant. So you can shuffle columns basically and not change the effect of the prediction. And so this is something along the lines of BERT, and it has been trained similarly with masked cell prediction. So to give a bit more details, this is like an outlook of the architecture. The bottom would be a row of a table. You can imagine this, so something very fake, very made up. And there are some columns which might be of date type, others might be of numerical type, others might be of text type, and so on. And given that traditional language models are not good at things like arithmetic or number, we instead built a custom-made tokenization for different kind of data so that they can be vectorized in a kind of more, if not smarter, at least more adequate manner for the type of data that you have. Once this is all done, then you are down to a standard sequence of vectors where now one token is equal to one cell. And you can do the standard thing that you did since time of birth, which is just feed it through a transformer. I mean, first mask it during pre-training, a random percentage of them, feed them through a transformer, and then output back something which looks like the input and compute loss, reconstruction loss of just predicting what you have. So this is a very high level, but we already have pre-trained a few models on this architecture based on, for now, I mean, we have both public and private data. Here I'm showing the public data. We have pre-trained on data from Wikipedia data sets, which amount to a total about 350 million tokens across 30 million tables. And then fine-tuned on a bunch of data sets that we took from this one paper that came out as ICML this year from researchers here in Paris called CART. And what we achieved in the end, it was to get a model which is basically on par with the state of the art, where the state of the art on this one data set is unsurprisingly CART, which of course is the paper that worked on this data set the most. But actually we also worked on improving some baselines. And since this is an AUTOML conference, you'll be happy to know that the strongest baseline we have is AutoGluon, which is actually on par with the state of the art. And also other model which is state of the art is CatBoost if provided with embeddings. So on the left we have accuracy datasets, on the right we have regression datasets, and within each plot on the left of this dashed line we have kind of the best model we could build, which combine both text embeddings and ensemble methods. On the right, we have models which are more standard in one way. So they are either doing assembling or doing text embeddings, but not both. And as such, I would say our model deals fares decently well. It performs better than the standard models, so let's say, and roughly on par or slightly worse than some, and better than XGBoost with the, let's say, more advanced models we could build. But of course, our work is still work in progress. We are aiming to publish something in a couple of weeks, but yeah, this is very much work in progress still. So please take these numbers with a grain of salt. And we also experimented a bit with scaling the model. So we scaled to different model sizes. As I said, the backbone is BERT architecture, so we could use the same nomenclature for a number of layers and the depth of each layer. We could scale size, and we could also compare training our model from scratch or fine-tuning the pre-trained model. So here the results I would say are a bit more mixed because yeah, both things, both scaling the size and pre-training help a bit, but help less than we would have expected. It might be because the pre-training data is very far away from the fine-tuning data being Wikipedia data, or it might be just because we don't have yet enough pre-training data. That might be as simple as that. But what is happening here is that, yeah, let's say we still have some work to do in this respect. But I mean, we, of course, ultimately, as SAP, we are not interested in open source data like Wikipedia, but we are rather interested in internal data that we have within our customers, which have two nice properties. On the one hand, it's much more data than Wikipedia data. And on the other hand, it's kind of more self-similar. So different tables are kind of human, non-readable, but they tend to resemble a bit to each other. And also, maybe to put this in perspective, with this previous slide, I only touched on the 2 points which I highlighted here. So we are trying to get high accuracy, and we are trying to scale down data a bit for the data needs. But for realistic SAP purposes, the data that we have is more something like this. So the tables on the left are very, very small extracts from real tables in SAP system. So you can imagine that instead of having 2 rows and 3 columns, you have something like 200 columns and 5 million rows or something, but it's something like that. And as you can see, they are completely non-human readable. You can see that these 2 tables here are related to each other because as a human, you see that, yeah, 2 columns are very similar or even identical. But unfortunately, they are not explicitly linked in the database. So as you might know, in a relational database, you have foreign keys that point from one table to the other. And you might expect that these 2 tables, given that they are part of the same sales, let's say, business concept, they are linked to each other, but in fact, they are not. There is a view on it, which is something external to these 2 tables that connects them together. And if you are an expert, then you know that this view is the right thing to look at, and it will give you, let's say, the correct join between multiple tables that give you some table on which you can actually work as a data scientist. But this is not, I mean, it is written somewhere in the whole of SAP data, but yeah, it's such a big data set, such a big database that you can't just look through all of it. And zooming out a bit, might look something like this. So you say that you're interested in a table field to the bottom, and you look at it, and it actually has several different columns in that, which are not human readable, don't really make much sense to you, and you want to resolve it in order to apply your preferred model. And actually, what you need is a connection like this. So as you can see, even from this plot, you have many hops to do. So in a kind of completely agnostic way, you would need to do a lot of joins to arrive to such a large number of hops in the graph to hope that the correct information is built in the data set. And once you do that, you would have so many columns and so much data that basically it becomes completely intractable, and that's not going to work. So what we would like to do, so from now on, I would say it's more mid to long term because there's not things which we have built yet. What we would like to do is to collect our business data and mix it with our business domain knowledge in such a way that this whole data can be encoded as a graph. And maybe then also add some LLMs on top that can enrich some of this data in the graph. And once you have these all built, at least abstractly, as a huge graph that goes through all of your of these database, S4HANA database, then you feed this for a graph neural network. And once you have this much data, of course, you have no labels, but you can train in a self-supervised learning way, for example, doing node prediction or link prediction on this large graph. And the hope with that would be that the model would be trained on so much SAP data that for SAP specific questions, it would be able to do predictions, ideally in a zero-shot way or maybe in context if you have a bit of data. But this is, yeah, it's quite far away. I mean, not quite far away, but it's kind of a long shot still. And we would like to get some cooperation, let's say, from the research world on this problem. But the problem is, of course, that to cooperate, you need data. Right now, we cannot really share data because it's, of course, customer data. It's not our data, and we can't just share it. So typically, there are two workarounds. Either it's some researchers kind of are embedded in a company. They sign NDA so they can work with the real data, look at it, but then they cannot really publish the result, or at least they can only publish highly anonymized version of data, which prevents other researchers from working on the same data and therefore doesn't really scale. Or conversely, people in the industry typically try to look for data sets which look close enough to what they have to work with. But at least in practice, we didn't find anything that vaguely resembles what we have actually in our system. One solution that we are trying to look at is to create a synthetic data set. So something that looks as close as possible to our own data, but that it is completely anonymized in a way that can be shared without problem and doesn't refer anymore to any specific customer of our own. This is, of course, a rather enormous task. So we have started on it, but it's still going to be rather long in the making. One thing which we are hoping to do a bit faster is to open source some real data set that we have internally. So this, like I said, is customer data. So we are in contact with the customer to get the green light to do that. Yeah, it's a legal process. It will take some time, but we are already ongoing with that. This is in the sales order auto completion use case, the same one that Johannes earlier showed in the UI thing, which would be the purpose would be to predict one specific class of the sales, one specific column of sales order. This is, I mean, the good side of this, of course, is that's true data, real data, so that the problems tend to be more interesting on real data than on synthetic data. The downside is that, of course, it's a much smaller scale, so it would only be a total of 4 tables linked as in the picture. So while there still has the same graph aspect, of course, you could just make a big join and just get one table and work on it. So it's still, in that respect, as a graph is still kind of a toy problem, but it's at least resembles enough the real problems that we have that it's a starting point. And also the scale of data is large, but not huge. It's like 3 million sales order items, which is large, but not very large for this. And these kind of things go. Yeah, then summing up what Johannes said, and he mentioned that working with data in a business context actually requires different expertise, both data scientists, but also, and maybe more importantly, experts on a specific kind of data that you use. The long-term hope is that we can build a foundation model that can do this in a self-supervised manner and can provide this expertise to everybody that uses it. We have some preliminary results, but they are still, I would say, rather limited due to the fact that we are working on a single table still. And on the mid-long term, we are rather going to look into graph neural network domain, where we hope that we could get more information from the whole graph. With that, I thank you and leave you up for questions.